Okay, welcome back. I felt that Friday people weren't really feeling how the optics stuff works, so I'm going to go into more depth about what we talked about in class on Friday in hopes that there is better confidence in that as we move forward. So you see the topics for today are basically the same ones as for yesterday. I'm using, Friday, the last time we gathered together. So let's just get right into it, get back to what we're doing before. So when we first saw this, it was called the mirror equation. Now it's called the thin lens equation. What's the difference in the mirror equation and the thin lens equation? There is none. It's the same equation. Now, one thing that is different here is there is not the radius equation. You actually have what we call the lens maker equation, 1 over f equals, I think it's n times 1 over r1 plus 1 over r2, where those are the radii of curvature of each of the two surfaces on the lens, and n is the index refraction the lens material is made out of. So it's a different equation to go from the curvatures to the focal length. There is one thing I need to mention that I keep forgetting. We're going to talk about in lab tomorrow, but that is the power of a lens. We have people here with eyeglasses. Does anyone know what their prescription is for their eyeglasses? Okay. Anna had her hand up. What?
-0.5 for both eyes.
-0.5 what?
I don't know. Oh, for like.
It's what?
Isn't the PPM? No, it's not.
It would be diopters is the name for it.
Okay.
And power is defined, the lens power. So this is a completely different thing than normal power. The lens power is defined as 1 over the focal length, where you have units of diopters are 1 over meter. So if your prescription is -0.5, that's what you said?
Yeah.
Then that means,
-1.5.
oh, 1.5. So if you have the power is equal to -1.5 diopters, that means that 1 over power is equal to the focal length is equal to 1 over -1.5. And then instead of diopters, I'm going to put 1 over meter here. So that's equal to 1 over -1.5 meters, or -0.75 meters. So it's a very straight conversion between the power of a lens and the focal length. And the only thing that really is tricky is that diopter is 1 over meter, because in class we're usually using centimeters for focal length. So in lab tomorrow, we'll actually have some fun and determine what your prescription is for eyeglasses. Of course, if you have contacts in, it kind of ruins that, but yeah, just wear your glasses. I was like, ain't gonna happen. Okay, where does this equation come from? From the equation. It comes from magic, as all things in physics.
Some person that was smarter than me came up with the equation doing experiments.
Oh, no. First of all, they probably weren't smarter than you. Second of all, they weren't doing experiments. It comes from geometry. It comes from this picture right here. So if we take an object, this distance right here is the distance object, right? This distance right here is the distance image. And if we take ray 2, does anybody remember what the name for ray 2 would be? It's the vertex ray. If we take that vertex ray, we are going to have a relationship that relates the height of the object, the height of the image, and those distances. Specifically, I have height object over distance object equals height image over distance image. Now you look at that, and at this point you're like, I don't see it. I don't see it at all, right? Because first of all, it's only two terms, and it doesn't have the focal length in it. So now I have to remember, what was the third part? If we take, and I'm going to take the right-hand side. If I take the right-hand side and I now take this triangle and this triangle, I'm going to have another relationship that says height object over distance object minus the focal length, since focal length is this distance right here, is equal to height image over focal length. So now I have two relationships between height object, height image, distance object, distance image, and focal length. And what I do, and well, what I like to do is just to say height object over height image is equal to distance object over distance image equals distance object minus f over f. So I calculate height object over height image for each of the two relationships. So that's equal to 1. And now I have an equation that I can solve. So I want to give everything a common denominator. And actually give them a common denominator. I'm trying to remember what the easy steps for doing this are. But it's this equation here that then simplifies to our mirror equation or thin lens equation. And so I'm trying to remember exactly how we would do this. If I divide both sides by DO minus, well, I'm not going to finish it out just because I didn't do it beforehand and don't remember what the step is. But bottom line is it comes from doing that geometry, from taking a couple triangles and relating them. So I want to remember, I said the point is to review how we do lens ray constructions for the image and to use that equation. So I'm going to go through each of the rays carefully and then do a bunch of examples. That's all we're going to do in class, going through each ray carefully and then doing examples so we see practice over and over. So the parallel ray. Parallel incident rays, by the definition of focal length, if you have parallel rays that come to a lens or to a mirror, they come and they meet at one point if the lens has the right shape, if the mirror has the right shape. And spherical isn't the right shape, but we approximate it. And so based on that, the parallel ray starts at the tip of the object and runs parallel to the principal axis. And then when it hits the mirror of the lens, it refracts, or reflects. So it goes through the principal focal point. Principal focal point being the place where parallel incident rays will meet. So that's our first ray, which we're going to practice over and over. I'm going to try to remember to do the parallel ray in green so it'll all be color coordinated. Okay, then the next one is the focal ray, which is exactly the reverse of the parallel ray. So the parallel ray, there we go. The parallel ray was parallel incident rays meet at the focal point. Light works the same forward and backward. Like Snell's law, it doesn't matter which one is medium 1 and which one's medium 2, as long as you have N1 and theta 1 together, and N2 and theta 2 together, it's going to work out. So the focal ray is doing the parallel ray in reverse. So you start at the tip of the object, and then you run through the secondary focal point. I had the principal focal point on the last one. Now I have a secondary focal point. What's the difference? The principal focal point is parallel incident rays meet at the principal focal point. The secondary focal point is if light starts at the secondary focal point and goes through the lens, it will come out parallel. For a thin lens, it's the same distance, opposite side. So you start at the tip of the object and go through the secondary focal point, and then it comes out parallel. Notice my little asterisk here. If the object is closer than the secondary focal point, then you start at the secondary focal point and go through the tip of the object. So in any case, you have a line that connects the secondary focal point and the object and goes to the lens or mirror, and then comes out parallel. The third and final one I'm going to talk about, I'm not going to talk about the center ray because it only applies to mirrors, is the vertex ray. If you have a thin lens, then at the vertex you have basically two parallel sides of glass or whatever it is. And so just like the problem you did in class where you showed that the incident ray going into parallel pane of glass was parallel to the exit ray after it came out of the parallel pane, you're going to have the light is parallel when it comes out. And if the lens is thin enough, it won't be distinguishable from having just gone straight and not had anything to do with the lens. So that is just going to be a straight line that just keeps going through the lens at the vertex where you have the two parallel sides. And if it's a mirror, well, it's going to reflect back symmetrically because angle of incidence will equal angle of reflection, and you have the principal axis as the normal. So those are definitions. Now let's do it, right? Because it makes a lot more sense doing it than it does in describing things. So I have 4 problems laid out here. And that's what we're doing. Oh, first I have a couple pictures. Different for, here's a normal converging lens with the object farther away than the focal point. And so you can look and see the parallel ray came in parallel, went through the principal focal point. The focal ray went from the tip of the object through the secondary focal point, continued, and came out parallel. And the vertex ray just went straight through the vertex and kept going.
What's the blue line?
Here, let me label for you. So the blue line is the focal ray. The green line is the parallel ray. And the red line is the vertex ray. Now, the second one that's already prepared that I'm not going to do is a diverging lens. Actually, maybe I'm going to do this. I don't know. With the object farther away than the focal point. Now, notice the principal focal point for the diverging lens is on the left side. That's negative in our distance table because that's not where transmitted rays should go. Whereas when we were looking at the converging lens, the principal focal point was on the positive side. Because you had a positive focal length, it's going out to the right. Negative focal length going to the left. But in both cases, both of these, you should mark both the principal and secondary focal points. And so usually you just use a capital F for the principal and a capital F prime secondary. But you should label those so you don't get confused. Go ahead, sir. Mm-hmm. Yes, diverging or converging. Concave means diverging.
So then on the picture above this, the primary focal point is past the lens.
Yes.
On the diverging one, the primary focal point
It's before. That's right.
Do you mind defining each of the rays while we're looking at the examples?
I will.
Okay.
Well, the ones I work out, I can do it on this one again. Here's your parallel ray. It came from the tip of the object parallel to the principal axis, then diverged through the principal focal point. Diverged because principal focal point was here, so you had to draw a dashed line and then just continue it. So there's no light where the dashed line is, but that's the direction that it's going to go after it refracts. Then we have the focal ray. The focal ray is going to the secondary focal point, which is on the other side. And so this here is a dashed line because no light is doing that. This here is what it actually does. And then it's extrapolated back because the image is where all of these rays meet. If the rays don't meet, you don't have a real image. But if the extrapolations meet, then you have a virtual image. And so you have the virtual image back there. And then finally, so this one here is the focal ray. That's RAY there, as you can totally tell. And then this here is the vertex ray. Probably the simplest to draw for a lens because it's a straight line going through the vertex and just keeps going. So the image is where the extrapolations in this case met, whereas for the real image, it was actual rays met at the image. So you can tell the difference immediately in your diagram if it's the actual rays that meet or if it's extrapolated rays that meet.
So,
Go ahead.
on the diverging lens, the angle it goes away is the angle as though light would have come from that point, but it does not.
Yeah. So like this here, this here is what the light really does. So that's really happening. This here is an extrapolation. Now I have these, and I was going to load them up on the computer beforehand, didn't have time. I was going to do them on this computer so it actually would work, because remember I tried it on my tablet, and the touch screen was defeating the ability to put things on. So let's get to doing some things. So 20 centimeter focal length lens, object 60 centimeters from the lens. When you're doing these diagrams, it's important that you actually measure distances. Don't just randomly draw stuff. It's important to use a straight edge. So this, I'm changed to using OneNote today so I can use a ruler. And so I put a vertical lens and I put a horizontal principal axis. And now I need to say, okay, where is my focal point? So if it's 120 centimeters, I have to decide on a scale. So I'm going to make 120 centimeters. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here is 12. It's kind of hard to do this with the ruler because you see the ruler wants me to draw a line. It jumps to that. So there's where my focal length is, or focal point, and then I have to do it on the other side as well. So 1, 2, 3, 4, 5, 6, 7, 8. Make sure I counted right. Yeah. So those are the focal points, the primary and secondary. And then my object is going to be located 60 centimeters from the lens.
Which side?
That's a very good question. By convention, we put our object on the left-hand side, and we have the light go left to right. That's a convention. Does it matter? No. Okay, so now I have the set for vertical. Put this on my object. Notice the problem didn't say how tall the object is. Usually it will tell you what to use for the object. So I'm going to make my object 2 whatever units high. You don't have to have the same scale for the vertical axis as you have for the horizontal axis. So you can choose those 2 scales separately. So there I have my object. We usually put a little arrow at the tip of the object. There's the object. And the focal points we had here was the secondary, and here was the principal.
How do we know that that's the order it is?
We know that because it's a positive number here. Since it's positive, that means that the principal is on the right. So now I'm ready to draw my rays. So the convention I was using was green for parallel. So I'm going to start with the parallel ray. Get that to 0 degrees, so it's actually going to be drawing correctly. There's my parallel ray going from the tip of the object to the lens. How does the parallel ray refract? Toward the principal focal point. So now I actually have to get this so it's going to the principal focal point from there.
Did you count like the 120 centimeters to view the focal ray or whatever? Or
to mark the focal points, I did, yes.
Okay. And there you can on this.
So there is the ray that is going through. That's the actual parallel ray. Now, because I know where this is going, I'm also going to, because I can't easily move the ruler around, I'm going to mark the extrapolation of that parallel ray back here. And I'm going to close it where I know the image is going to be. Okay, so I have the parallel ray complete. Parallel ray. So now I will go to the focal ray. What was our rule on the focal ray?
Start at the secondary.
Tip of the object.
Okay, tip the object to
Secondary.
secondary. So tip the object to the secondary. Well, they're in reverse order. That's why I had the asterisk. So it's going to be like that. So this here, there's no light actually doing that, right? Because it's coming from the tip, goes like this. And how does it come out? Comes out parallel. I hear wait. That is the secondary focal point, yes.
That one with
The one with the prime, yeah.
I got the second. It's got a one line as the secondary.
Because the primary doesn't have a prime. It's a prime like an apostrophe. It's a standard. So it comes out parallel. Well, now you can clearly see the green line and the blue lines, they will never meet. But I knew that. That's why I extrapolated back my green line. Now I'm going to extrapolate back my blue line. So now I have my focal ray done. And all that remains is the vertex ray. Vertex ray, the easy one, from the tip to the vertex. Okay, 17 is not working. 18, yeah, 18 will work. So it just goes like this. And of course, that never meets the other two, so I extrapolate. And now, as you can see, with a carefully drawn picture, they actually do all meet the same place, which is what's supposed to happen. So you can see the difference in me freehanding it and not coming close, probably not giving you much confidence, to doing it with a ruler, and it actually meets. So
This is a virtual image.
that is correct. How do you know it's virtual? What was your hot tip there?
Because the image is based on the extrapolated, not based on the actual light. Like the actual light doesn't meet where the image is.
Correct. So there is my image. There's an A in image. What words would be used to describe this? That's upright or inverted and real and virtual. Andy already said virtual. Why virtual? Because the rays don't really meet there. And is it upright or inverted? Upright. So we have an upright virtual image.
Would we also say that it's magnified or no?
Yes, we would.
So because the rays don't meet, that's how you know it's virtual?
Yes.
Right.
Yeah, it's an extrapolation rather than the actual rays. Excuse me? It's upright because my arrowhead was pointing up and it's pointing up again. Now, in terms of magnification, at this point, you would use your ruler to measure the magnification. So this one here is 1, 2, 3, 4 of my units high. So I have height of the image is equal to 4, whatever the units were. Height of the object, I had told you and measured it before, is 2. And thus the magnification is height image over height object equals 2. And that should also equal from the math I did up here, that should also equal, well, this is upside down because it's object over image. It should also be distance image over distance object. Except for it's minus distance image over distance object. So that was all done ray tracing. And if you have questions about the ray tracing, of course I'm going to do more examples, but if you have questions, ask them, because I want to make sure we understand this.
So the image is formed at f prime, which we know is
In this case,
negative 120 centimeters. So
Yes.
the distance of the image of the object would be negative 120 over 60. So 2.
that's right. Now I want to do this mathematically as well. Most students are much more comfortable with the mathematical method, but I'm going to be grading you on this diagram if you did this part right, not on if you can do the math right for the one question that says to draw the diagram. So if I'm going to do this mathematically, the numbers we had were focal length equals 120 centimeters, distance object equals 60 centimeters, and then we have our thin lens equation. Since I'm looking for distance image, I'm going to solve this. 1 over distance image is 1 over f minus 1 over distance object. So distance image is equal to 1 over f minus 1 over distance object equals 1 over 120 centimeters minus 1 over 60 centimeters. 1 over 120 minus 1 over 160. Common denominators, or not 160, 60. Common denominator is 120. So that's 1 over 120 minus 2 over 120. So it's negative 1 over 120. 1 over negative 1 over 120 is negative 120 centimeters. And so that's our distance image. Looking back at the picture, my focal length was 120 centimeters. The secondary focal point was at minus 120 because it's on the opposite side. And so it should be right on that secondary focal point. I'm off just a little tiny bit, but that's it's pretty much as exact as I'm ever going to get.
So we wouldn't get, like, you don't have to do the math on this problem that we're going to do on
Correct.
this.
Correct. I'm doing the math so we can see it done both ways. So that's the distance image, the magnification, and this is just going back over what Andy worked out verbally. Magnification is equal to the height of the image over height of the object equals minus distance image over distance object equals minus 120 centimeters over 60 centimeters equals 2. Now, we call this sometimes the lateral magnification. At this point, we're just calling it magnification. But when we talk about what we're supposed to be talking about today, microscopes and telescopes, we'll talk about angular magnifications. So that pretty much covers what you can do in a problem like this. I'm ready to go to a second one unless somebody wants to ask any more questions about this example. All right. Next one, minus 120 centimeter focal length. Minus 120 centimeters, what does that tell you?
It tells you that the primary focal length is on the left side and the secondary is on the right side.
Okay, it tells you that it's a diverging type, and so exactly what Andy said. So I should have, well, actually maybe I shouldn't have. I should have done it like I just did because it's the best way to make sure you remember where everything came from. Let's try the highlighter for the focal points this time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's a little wide, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then for my object will be 5 centimeters. That was supposed to be 60. I changed numbers because I was going to show an example using the PHYS website from Colorado. And I found that I could do those, whereas the 5 wouldn't work out. 1, 2, 3, 4, 5, 6. So there's where my object is.
Is your little thingy the object or the focal point?
I recognize your question. The principal focal point is the one I just labeled with capital F. The secondary focal point is the one I labeled with the F prime. And then my object is going to be where that is.
I'm still so confused as to whether it's on the right. I guess I just have to memorize that.
Well, it's easy for me to say yes and move on, but the key is if you have parallel rays coming in, where do they meet? If they're parallel rays from the left, wherever they meet is the principal focal point. So if it's diverging, they don't meet on the right, but their extrapolations meet on the left. Whereas if it's converging ones, then they'll meet on the right. So that's how you get the principle is if I had parallel rays coming in from the left, where would they meet? The end outcome is what you said, left for negative, right for positive. So if it's converging with a positive focal length, then it's going to be on the right. If it's diverging with a negative focal length, it's going to be on the left for the principal. So I have my object, I have my focal points. The only difference between this diagram and the last one is which side is the principal focal point and which one is the secondary.
Is the object always going to be on that side?
By convention, we always put the object on the left side of the lens or mirror. So how do I draw my parallel ray?
From the tip of the object through the vertex to the focal point.
Not to the vertex.
Yeah, so it doesn't go to the vertex in this case.
It just goes parallel to the principal axis. So it goes like this. And then how does it refract?
It goes back to the focal point.
Okay, it goes. Now what I said before was it goes through the principal focal point. Well, now the principal focal point's on the wrong side. And so I draw it as if it came from there. There's an extrapolation. So there is my parallel ray. It doesn't look the same, right? It looks different because the principal focal point was on the other side. Next, the focal ray. So the focal ray, how does it start? From the tip of the object to secondary focal point. So now the secondary focal point was on the other side. And, okay. 7 is a little too steep. 6. I can't do a half. 6 is a little too flat. I think 7's closer. So once again, you can see it's not going to be just right because I can't get my angle just right. What's wrong with what I just drew? Yeah. It doesn't go through like that. So I'm going to not draw. I'm not going to draw that set of dotted lines just because I think it adds to the confusion. Comes like this, and then how does it refract? The focal ray comes out parallel. So it's going to come out parallel. Well, clearly those two don't meet. So I'm extrapolating back. Maybe.
Wait, you don't extrapolate from the tip of the object?
The solid blue line is the complete what light does.
Okay.
And then the extrapolation is the extrapolation of what the exit ray was doing. So that's why I didn't draw the additional one. If you looked at the picture carefully, you saw they had a black extrapolation for that because it's not an extrapolation of what the light does. It's an extrapolation of how I drew my first ray. Okay, so where's the image formed?
It looks like it's going to be formed
I'm going to do one more, yes. But
on the same side because that's what they're already crossing.
okay, they're crossing. You can see they're crossing here. So it's going to be formed there, but I want to do the third one just as the check. That's why you have to do 3 for the test problem, because you want to have the check to make sure, yeah, it wasn't just, well, there's 2, good enough, we're going to go with it. So the vertex ray does that. I don't need to do a backward extrapolation because that's exactly what it does. The backward extrapolation comes back right on itself. So the image is formed about, Okay,
so for this one,
go ahead.
one of the lines is real and the other 2 are.
It's both real and extrapolation because it's a straight line, so the extrapolation comes straight back on it.
Right, so then it's still a virtual image though, right?
Correct,
Because
correct. Yeah, I see the confusion because there really is a light ray that I used to construct this that went through that point. But the other 2 extrapolations, so you have to have them all
you
meet.
have to have them all meet
Yeah.
to be relevant.
So we have here virtual, as she said. Is it upright?
Yes.
Magnified?
No.
Diminished.
How do we know that?
Because it's less than 1. Smaller size. So now I can measure the height. Once again, I started with a height of 2 of these divisions, and now I'm at about 1.5. So the height of the image is 1.5 divisions. The height of the object was 2 divisions. So the magnification is 0.75. I didn't want to write on top of my ray, so that's why I shifted down. So that's what I get from my ray tracing. Once again, this is what you would need for the test problem that says show with the ray tracing. Doing it mathematically, minus 120 centimeters. Distance object is equal to 60 centimeters. Doing the same as I did before, distance image equals 1 over minus 120 centimeters minus 1 over 60 centimeters. That's the same as I had right there, except for changing the value for the focal length. But 1 over 120, negative 1 over 120 minus 2 over 120 is minus 3 over 120. Invert that and it's 120 over 3. Okay? Here's the intermediate math. I multiplied the 1 over 160 by 2 over 2. And so that's equal to 1 over minus 1 minus 2 is minus 3. Using the invert and multiply rule gives me that. Using the invert and multiply, 1 divided by. And so 120 divided by 3 is 40, right? Minus 40 centimeters.
On the last one, I got positive.
For what?
The last one was
For,
not positive.
for the one that I just did or the one before it?
The one before.
Okay, so the one before it, this was 1 over 120 minus 2 over 120 when I give them a common denominator.
Yeah.
So 1 minus 2 is a negative 1.
But then we plugged it into an equation with the negatives that became positive.
That was for magnification. Yeah, for magnification, not for the distance image. So doing that right here, magnification is equal to minus distance image over distance object is equal to minus 40 centimeters over 60 centimeters, and I have 0.67. So my estimate of 1.5 and 0.75, you see, was a little off from the actual what it should have been. But you stick with what you drew. You don't say, oh, let's go back and fudge numbers. It was the best of my drawing within the limitations of my ruler. Is what? Okay. Any questions about how I did this one? No questions? The next two are the same thing, but with a mirror. So here I have a 240 centimeter radius mirror. The object 60 centimeters from the mirror.
That means everything's going to be reflected back, right?
Correct.
Okay.
So once again, I got to draw my focal point. Notice I just said focal point.
We don't have two, right? Because we can't put.
For the mirror, you don't have two. You only have one because all of the light is going to be on the left-hand side. And so I just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I'm trying to make it centered on the right mark. And my object at 6. 1, 2, 3, 4, 5, 6. My object. So I have purple. I don't have an F prime, I just have F. Principal and secondary, the same place. And then for my object, go ahead.
At 120 because the focal length for the mirror is R/2.
Oh, thank you. Yes, that was intentional, and I forgot to say it. Since focal length is equal to 1 over R, or not 1 over R, R over 2, that's equal to 240 centimeters over 2 equals 120 centimeters. Right, I wanted to just get the same geometry every time.
Oh.
So there's my object. Parallel ray. Where's the parallel ray going to go?
It goes parallel to the vertex and then bounces back to the focal point.
In many regards, it's easier to do the mirror one because you don't have to say which focal point.
Are we going to extrapolate lines from this one?
Sure, why not?
Okay.
It's never going to hurt me, right?
That's-
So there is my parallel ray. Welcome to my world. All right, next the focal ray.
Extrapolate it if you know it doesn't occur.
Because if we have a virtual image, it's going to be based on the extrapolation. So I said, what's it going to hurt? And the truth is, all of the cases I chose for today are virtual.
Wait, so, where's the vertex? Do we have to talk?
The vertex, I will get to it. It's going to be the third one, but the vertex is right there.
Oh, never.
Okay, so focal ray. How's the focal ray work? Tip of the object. Then what?
To the focal point.
Okay, so that means it's going like right. I'm not drawing that extrapolation this time again, just because that's how I got the direction. Right, I went from here up like that to get the direction. How does it reflect? Parallel. And now we can see, oh yes, the blue and the green, they do not meet. So the extrapolation is going to be useful here. And my third ray, the vertex ray.
That goes from the tip to the vertex.
From the tip to the vertex. This one is not as easy as it was with the mirror, because with the mirror it was a straight line. Or with the lens, yes. Notice that's 19 degrees. I'm going to go to 19 degrees downslope instead of upslope for the continuation. How I normally do this is I just measure the height of the object and put a dot down below where the tip would be if it was inverted and go through that point.
Okay, wait, say that last thing again. Like, we know.
I will show you. I'll show you.
Okay.
So here is my vertex ray, and then of course the extrapolation. Not as good this time. So as I said, what I would normally do, bring this back to vertical, and I made my line so it was 2 divisions up. Actually, it's a little more than 2 divisions up because I was sloppy. And so I would make a mark down here at 2 divisions and a little bit more because I was sloppy below. And then I would go through that point to make sure I got the angle right for the reflection. So there's the way that the vertex ray goes. I forgot to label the focal ray. Where's the image? Where they meet. Now, if you look at this, I was just the red one. Just the vertex ray was bad. But because the vertex ray was bad, I get crossings that range between those 3 points. I always just say, let's take the intermediate of the 3. Even though I am pretty certain that where the green and blue intersect is probably where it should be, I'm just going to say I did 3 to the best of my ability, even though I have good reason to believe this one's the bad one. I'm just going to go to the middle position between the 3 and draw my image there.
It's virtual, upright, and magnified.
I'm going to actually measure the height here while I'm at it. I started with a height of just over 2, and now it's just over 1, 2, 3, 4. So I can put height image is equal to 4, height object equals 2, magnification is equal to 4 over 2 equals 2. It's virtual, upright, magnified. At this point, you should have noticed a pattern. If it's a virtual image, it's upright. It was magnified in some and diminished in some, but it was always upright. Likewise, if it's a real image, it's always going to be inverted, which means your magnifications are always going to be negative for the real images. I see from you putting books away that my time is just about done. If I do the math, this math will exactly repeat the first one I did. All right. Have a great Monday. I'll see you in lab on Tuesday, and we'll talk about the eye and vision.
So is lab tomorrow going to be like the lecture?